All right, so we're starting by taking a look at this situation where we know the following three pieces of information. So we know that f of a equals f of b. What's that really telling us? When I write f of a equals f of b, what's another way to describe that in more conversational terms, less technical? If f of a equals f of b, that means the y values are the same. So the y value at a is going to be the same as the y value at b. So in other words, if I connected these two with a line, it would be a horizontal line. All right, so they start the same height. Then we also know that f must be continuous over the interval, and we must know that f is differentiable over the interval. So the question is, can we know that the slope must equal 0 at some point? Yeah. Well, if I did just connect them with a line, does the slope ever equal 0 here?
No.
Yeah.
Oh, wait, yes.
What's the slope here? 0. Yeah, if it's a horizontal line, the slope is a constant 0. So yes, we can know that. So now we need to start goofing off and seeing what else we can do. If I do this, does the slope of that ever equal 0?
Yes.
Yes, be somewhere up here. What about if I go down here?
Yes.
Yep, okay. Of course, we could do other stuff along the way here, right? Does the slope ever equal 0 there? Yes. Okay, so then what about that? Does the slope ever equal 0 here?
Yes. On the left side. See how it dips down a little bit and then goes up?
All right, that's a little close, yeah. There. Does that slope ever equal 0? No. But is this graph possible with this situation?
No, it's not continuous.
Yeah, this one's not continuous, and it's not differentiable at a given point. And so that ends up ruling it out. So can you think of a way now where we could draw a graph that meets all three requirements,
No.
but we would never hit a slope of 0? So the question comes up, could we do this? Well, at corners it's not differentiable. Yep. So close, but not quite. So yeah, I mean, we've been talking through it. We've been trying to figure out any other ways that we could do it, but we haven't come up with one. If f of a equals f of b, so they are in fact at the same height, then it doesn't seem like there's any way that we can meet these requirements without knowing that the slope will hit 0 at some point. And in fact, there's big, long, complicated proofs that can prove that that must always be the case. And it all comes under the umbrella of something called Rolle's theorem. And so this needs to go into our notes then. Now, Rolle's theorem here, there's notice 3 different requirements. These were the 3 givens in the last problem where we were looking to see if we could find a counterexample, and we couldn't. But it's the same one. So if we know that f is continuous on the interval, that it's differentiable on the interval, and that our 2 y values are the same, then we can know that at least at some point the derivative is going to equal 0. And we can actually find out where if we know the equation and all that kind of stuff. Now, a couple of details. You'll notice that it must be continuous on the closed interval, but only differentiable on the open interval. What that does for us is that allows us to include endpoints. Like if I'm considering a square root function, I could actually consider what's happening here at the start of it, because it's continuous on the closed interval, for instance between here and here, and it's differentiable on the open interval, because it's not differentiable at that point, but by making it the open interval, it doesn't have to be differentiable at the point, just as close as we can get to it as possible. And so that's why we have that little bit of variation between the open and closed intervals there. So we're going to be practicing Rolle's theorem with a number of examples. This is the first of those. So we know our f of x function in this case, and in order to use Rolle's theorem, notice the first thing we do is we need to verify that it satisfies the requirement. And so that means we need to know, is it continuous on the interval from a to b? So this is a polynomial function. Is it continuous? Yes.
Yeah.
All of our polynomial functions we can know are continuous actually from negative infinity up to infinity, so it's going to be on the whole thing. Same is true about it being differentiable, actually. It is differentiable on the whole thing as well, because there's no corners, no asymptotes, nothing like that that's going to cause any problems. Really, the one that tends to make any determinations here on whether we can or can't use Rolle's theorem in this case, that we really got to check closely, is this. Does f of a equal f of b? In order to answer that, we actually have to do the calculations. So we're going to have to actually figure out what does f of 3 equal, and what does f of 8 equal. Because when we talk about a and b, that's our interval. So a and b is talking about the 3 and the 8. So plug in the 3. If we plug in 3, that ends up giving us 9 minus 33 plus 30. Add them together, we get 6. Now, in order for us to be able to use Rolle's theorem, this next one will also have to be 6. We got to plug it in, we got to check it. So plug in 8, you get 64 minus 88 plus 30. Add them up, we do get 6. And so, yes, f of 3 does equal f of 8. They both equal 6. And of course, yes, we know it's continuous and differentiable as we talked about. So now, that was the first half of this. The first half is just verify that we can use Rolle's theorem. But Rolle's theorem tells us that there is some value c where the derivative equals 0. So basically, when it says find c, what it means is figure out where does f prime of x equal 0. So please go ahead and find that value. All right, so we find our derivative, which is 2x minus 11, and then we solve that for when it's equal to 0. You should have found here that x equals 5.5. So that is our c value. We end up finding that c equals 5.5. C is just the chosen name given to it for basically saying the value at which our slope is going to equal 0. All right, I'd now like you to practice this process on this problem. So, first of all, let's go through our run here. Is it continuous on our interval?
No. Yes.
It's a polynomial, so yes. Then, is it differentiable? Yes. It's a polynomial. Every polynomial you can know right away is going to be continuous and differentiable over our intervals. But then, we have to check and see if f of a equals f of b. So we're going to do f of negative 4, and we're going to be doing f of a positive 4, and figure out what both of those equal. When we do that, are they the same? No, you actually need to plug in the numbers and find out.
I did.
In this case, they are not equal. Now, that means that we do not proceed on defining the numbers. And so, at this point, we've proven that we cannot use Rolle's theorem. Well, it is possible that there are points where it would actually hit 0. All we've done here is prove that we can't necessarily prove that it will. It still might, but we can't know it for sure at this point. All right, next up, I'd like you please to apply Rolle's theorem to this. So first of all, verify if we can use Rolle's theorem, and then if we can, find the values of c. Now, let's start with the first two here really quick together here. Is it continuous and is it differentiable over our interval from 0 to pi? Yes, it is. In fact, sine and cosine graphs in general, if it is just sine or cosine, it is continuous and differentiable from negative infinity to infinity. So whatever our interval is, it's going to work. But we still do have to prove this, so then go on and actually check, does f of 0 equal f of pi? So we find f of 0, we find f of pi. You should find that both those equal 0. So we can go ahead and know that somewhere in our interval that the derivative is going to equal 0. But that means you actually now need to solve it. Figure out what does f prime of x equal, and then figure out when does f prime of x equal 0. So, in order to do this one then, we find our derivative, which is 2 times cosine of 2x. Remember, you still got to use chain rule with it.
No.
And then I can go ahead and divide both sides by 2, though. So, actually, if you forgot about the 2, it's still going to equal the same values. But we need to figure out, where does cosine of 2x equal 0? Well, of course, we know our cosine graph, right? In the case of cosine of 2x, it tells us that this point where it ends out here is actually at pi. This is all going back to unit circle. And so, normally, if it was just cosine of x, we would know that it'd be hitting 0 at pi over 2.
But is that the period?
In this case, though, it's half as much, so it's at pi over 4.
The amplitude.
And then the other one is at 3 pi over 4. Now, notice I can stop at pi. It, of course, hits 0 an infinite number of times, but I only care about, remember, the ones that are between 0 and pi. So there are actually 2 solutions here. Pi over 4 and 3 pi over 4. And so, in order to do this one, we need to be answering the same questions, of course, right? So, first of all, is this function continuous?
No.
Well, remember, it's a question of, is it continuous over the interval? Now, from negative infinity to infinity, it is not continuous, because we can see that it's going to have an asymptote or a hole at that point. Now, what x value will that be at, though? Negative 2. That's outside of our interval. So actually, it is continuous then between negative 1 and 3. So we're okay on the continuous part. Basically, like if we're just looking at the graph, it's like we're just looking at the part on the right side. So we're looking at kind of like the right side of a rational expression. It's that sort of thing that we're looking at. Okay, so because we're just looking at that one section of this graph, it is both continuous and differentiable, because this is not interfering with where the asymptote would happen. Now, if we change the interval to include the asymptote, then we wouldn't be able to go further. But we still need to check, does f of a equal f of b? So you plug them in. So when you plug in negative 1, figure out f of negative 1, what do you get as an answer? 0. Okay, then we check f of 3. When we plug 3 in, what do we get? 0. They both equal. So that means that yes, in fact, we will end up being able to do this, because both of them, when we plug it in, it ends up being 0 over a number. Either 0 over 1 or 0 over 5. Now that we've proven that Rolle's theorem is possible here, find the values of c. So in other words, figure out now, where does the derivative equal 0? Yes, that means find the derivative of this function. So when we go to find our derivative here, we'll find the derivative of this rational expression. In order to do that then, we have to use quotient rule. So, low d high minus high d low, all over the square of what's below. Find that now, please. So when we set up quotient rule, this is what it ends up looking like. And now we got to be able to solve this, right? Now, if we're going to have to solve this whole thing, we got to simplify it first. So go ahead and simplify this. So multiply out the parentheses on the top. Distribute the subtraction. Clean it up as much as you possibly can, and then we can worry about solving it. Because there will be actually a little bit of a different technique in how we solve it, and I want to make sure that we get to that point first. So we go ahead and we multiply out our binomials here. But then remember what this subtraction does. This is actually one of the big traps when using quotient rule, is that we might forget to distribute in that subtraction. Notice that flips all of the signs. All right, now that we've gotten to this point, we can go ahead and combine our like terms. You should end up with x squared plus 4x minus 1 all over x squared plus 4x plus 4. And we then need to go ahead and solve this. We need to solve it to where it's going to be equal to 0. Now, can we simplify this at all? Taking a look at the top, can we factor it?
No.
No, that one's not factorable. So there's no way I'm going to be able to combine it with this factored form on the bottom, because we know that factors to x plus 2 squared, but it doesn't actually matter because the top isn't factorable. So there's nothing we can cancel there. Little side note here, because there's always somebody who ends up wondering this. Can I cancel out the x squareds?
No.
No, because remember, in order to cancel something out, I'm dividing it out of every single term on top and bottom. All right, so now that we've gotten to this point, we need to be able to now solve this. Now, there's two things we got to deal with here. In order to make a fraction equal 0, of course, we can just set the top equal to 0, right?
What?
So if I make the top of this whole thing equal 0, 0 over anything will equal 0, right?
Sure.
Kind of. This, the bottom, it cannot equal 0, remember. If I plugged in numbers and ended up getting 0 over 0, would that equal 0?
No.
No. That is undefined. Even 0 over 0 cannot be done. So we're going to need to be able to figure that part out as well. So basically what we're going to do now, in order to solve this, is we're going to break this up into two separate equations. We're going to figure out where our derivative is undefined by setting the bottom equal to 0. And we're going to figure out where the derivative equals 0, which is really the part we care about, by setting the top equal to 0. Now, the undefined part, this is just going to tell us what x can't equal. So it's going to eliminate anything here. Theoretically, though, we shouldn't come up with an answer. Basically, this is a way for us to be able to check ourselves. So if I solve this through, remember, I already know how to factor that. That is x plus 2 squared. That's where it came from. And if I solve this, I end up finding that x would equal -2. Is this in my interval? No. Okay, why did I do that? I just confirmed that I didn't make a mistake earlier. If this were in my interval, then I would now know that I made a mistake earlier, and it turns out it's not actually either continuous or differentiable at -2. So really we are just double checking ourselves there. The real work of this one now is setting this equal to 0 and solving it. All right, we already talked about if it was factorable. It's not factorable.
So,
How can I solve a quadratic if it's not factorable? We need to use the quadratic formula here. So use the quadratic formula and now solve this to figure out what x would equal. And so when using quadratic formula, remember at this point we got two different options. We can give our answer exactly, or we can give our answer as decimal. However, remember that we're looking to see what's happening in this particular interval. I mean, I could give an exact answer. It looks like it would be -2 plus or minus √5. But is -2 plus √5 between -1 and 3? You probably don't know that off the top of your head. So you don't actually want to give this as your final answer. You actually want to get the decimal values here.
not the negative.
When you do these calculations, you should end up getting that x is about 0.24 and -4.24.
Oh, get it out.
Now, notice between the two values that we just found, only one of them actually is going to fit within our actual interval that we are given. And so that's the only answer. So in the end, this is the C value. The C value is about 0.24, or in other words, -2 plus the square root of 5.